Hello, everyone, and welcome back. In the previous lecture, we introduced an alternative method for finding the volume of a solid of revolution. It's alternative to the method of slices that we saw previously, and we termed this new method the method of cylindrical shells. And in the previous video, we did this with a specific example. So the goal of this video is to extend it beyond just a specific example and see how we can apply this thing in practice to a broad range of functions and solids of revolution. So let's take a look. We remember that the basic idea here is that we want to define an area in the plane and sweep it around some axis in order to create a solid object. So let's say we are given a continuous function, which is non-negative, and we form the region, or we will revolve the region between f of x and the x-axis between, say, two endpoints. We've seen it over and over and over again, A and B, around let's say some vertical line x equal to L. And to keep our lives simple, we will assume L is less than or equal to A. So we're rotating this thing around some vertical axis that's to the left of the endpoint. Now, you can do this with L larger than B as well. That's perfectly fine. And I hope that you can extrapolate based on what I'm going to show you here. But let's keep it simple for now. Okay, so then what did we do in the previous video? Well, we basically formed Riemann sums, right? So if you think of what you do with the method of slices, you first form the object, then you take slices, you find the area of the cross section, and then you turn it into this sort of Riemann sum type thing, and then you take the limit, you get a definite integral. And the definite integral is over all of the area slices. The alternative method that we talked about in the previous video was this method of cylindrical shells, where first you do the Riemann sum and then you do the revolution. So if we're going to start with Riemann sums, we're going to start in the same way that we've been starting for anything that was covered in chapter 5. And so let's imagine, let's take some delta x to be the length of the interval divided by n. So the way that we usually start this out, and partition the interval AB by A, we'll call that x0, sorry, is strictly less than x1, which is strictly less than x2, all the way up until we get to xn, which is equal to b, where the gap between any two of these points is exactly delta x. So we just partition this interval into a bunch of little sub-intervals, the same thing that we've been doing with Riemann sums. Now, one of the things that we saw with Riemann sums is that we take some point. So we're going to say let CK be a point in each one of these intervals. And this point is going to be used to find the height of the rectangle that forms this Riemann sum. So here's the basic idea. So the Riemann sums have height f of ck, or sorry, the rectangles underneath have height f of ck. They have width delta k. And remember, we're going to sweep this thing around. So you take each one of those little tiny rectangles sweep it around, and it traces out a hollowed out cylinder. And so the question is, what is the volume of this hollowed out cylinder? So let VK be the volume of these cylinders, the kth cylinder. So the cylinder formed between xk minus 1 and xk. Then we saw that when you unravel these things, they can be turned into rectangles, or they're actually rectangular prisms. They're three-dimensional objects. They have depth or thickness, delta k. They have height given by f of ck. And then we remember the length here was given by the circumference of the cylinder. And in this case, we're going to use the circumference given by the ck term. So this tells us, let me write this, 2 pi, and then times the shell radius, right? So that's the circumference right there, 2 pi r, and then times the shell height, and then times the thickness. So again, if we just want to think about this, if you go back to the previous video or your notes from the previous video, and you think about how we unraveled that thing, we just got that nice little rectangular prism. So here, what is it that we have? Well, the shell radius, this is going to be where the ck is. So in this case, it's sort of an average shell radius. Again, everything's being taken in the limit, so it doesn't really matter. We can sort of fudge some of the details here. But we're going to think of sort of the average cell radius, and this is going to be given by the distance from ck, which is above A, to the line of revolution, which is x equal to L. So that will be ck minus L. Okay, so the sort of piece in the cylinder that you're using to form the height, and then all the way back to the point where you're revolving this thing around. So you're just going like this. So you think of that as sort of the average shell radius. Okay, next step, the shell height. This is just coming from the Riemann sum. So this is f of ck. And then the thickness, this is your delta x term. And so you think of this as, for every single ck, you get a little shell. And then, sort of like Russian nesting dolls, you build these things on top of each other until you get a nice sort of step function, discrete approximation of a nice, smooth, continuous three-dimensional object. So that tells us that the volume of the object, or volume of solid of revolution, is approximately given by summing up all of these volumes of the cylindrical shells. So this is running from k equal to 1 all the way up to n to vk. Right, so this is sort of like approximating the volume of an object by filling it with stuff that you know the volume of, right? So if I have a big glass jar and I fill it with 100 marbles, and I know the volume of the marbles are, I don't know, 1 centimeter cubed, then I can approximate the volume of the jar to be 100 centimeters cubed. That's the same idea. You're packing in as much here, and you're packing it in extremely densely when n is very, very large. And so this gives us a Riemann sum. So then, passing to the limit, delta x goes to 0, which is essentially n going to infinity. We get that the volume of the solid of revolution, so I'm just going to call that V, just so that I don't have to write that huge sentence. So equals V. This thing is equal to this limit So if we just write it so we can actually see the Riemann sum sort of popping out of it, it's nice just to have that little visual cue. Well, this thing gives me the integral from a to b of 2 pi times the shell radius times the shell height and then the delta x becomes that infinitesimal dx. So what you can think of the process happening here is that the shells are becoming infinitely thin, right? So it's just like little pieces of infinitely thin sheet metal that are sort of stacked around each other to form these Russian nesting dolls. And so, if we put in what we know here, we get the integral from a to b. Now the 2 pi stays the same. The shell radius, now the shell is centered at x. It has no width. There is no variation off the value of x. So that means that my ck term becomes x. So I have x minus L. And then the height is f at ck because ck became x. I get f of x dx. So now I've got myself a nice little formula here that I can use to find the volume of these things, and I don't have to rederive it every single time using the Riemann sum. And I want you to be careful here. I'm using x. Now, we always think of x as being the horizontal axis, but it doesn't have to be, right? We can rotate these things around some vertical or horizontal axis as well. And we've seen it, we've done it, we're going to do it again today. So you should think of x really as like a thickness variable, okay? So that's what we call x. We say x is sort of like a thickness variable. And if you're thinking yourself, Jason, you just made this way more confusing for me, well, it's not okay, but it's okay for now, because by the end of the video, I think that things will make much more sense for what I'm talking about. And of course, they only make sense really when we start doing examples. So let's kick it right to an example here. So example 1 for today. This is actually an example that we've already done using the slice method. So let's see, if the volume never changed. So if we already calculated the volume, we should be getting the same answer as we got before. So let's say the region bounded by the square root function, the x-axis, and the line x equal to 4 is revolved around the y-axis to generate a solid. Generate a solid. And of course, the usual question, find its volume. Okay. First place we always start with these things is a sketch. We have to always start with a sketch just so we can get our head around what we're sort of dealing with here. So let's take a look. Okay, my square root function. I have to be perfectly honest here. I really like examples that involve the square root function because it's one of the few functions that I can actually draw well with the iPad here. It's the only one that doesn't come out all shaky and ugly so far. So I really, I'm going to try and steer us towards more of these examples. Okay, so we're bounded on the right by 4. We can see that we're bounded on the left by 0 since the region that we're rotating around has to be trapped between the curve and the x-axis. And finally, we are rotating around the y-axis. So just like this. So the first thing is to identify all of the components that we need, right? So we know that the endpoints, we might as well just write things down that we know. Well, A is equal to 0 and B is equal to 4, right? So we just identified that. The axis of revolution, so where we're revolving around, this is the y-axis. This is given by the line x equal to 0. So that tells us that L value, so if I run back here to this other side, the L value is equal to 0. So I've already got a nice little simplification, right? Things aren't maybe as messy as they could be. Oh, sorry. Okay. So now the question is, what are the rest of the pieces here? Well, it's relatively straightforward, right? Because if I pick some value of x in this thing, then I'm going up to f of x. And what you can imagine happens in the limit here is I take that line and I sweep that line all the way around the y-axis to get this sort of infinitely thin little cylinder that has it has a radius given by, maybe I'll try and use a different color for this. I don't know how hard yellow will be to see. Its radius is given by x. Its height is given by f of x. And so that means that the volume of this thing, when I put in all of the components that I have here, is a definite integral from 0 to 4 of x. Sorry, I forgot the 2 pi already. It's 2 pi x, and then times the height, which is the square root of x. Now we've got all the pieces we need, right? Now it's just, I'd like to say a calculator problem, but it's not a calculator problem, right? It's just a straight sort of basic integral calculus problem. So we boiled it down from a word problem to a nice thing that we can solve. And so this gives me the integral from 0 to 4 of 2 pi x to the 3 over 2 dx. This is a nice, relatively mild integral. I don't want to call it easy because there's still a little work to do, but I get a nice 2 over 5 here, x to the 5 over 2, and this runs from 0 to 4. Now, plug that into your calculator, 128 over 5 pi. So we've got a nice, easy solution here. That was, the hardest part about this thing was boiling down all of the pieces and putting them into that integral. But once they're in the integral, things are relatively straightforward. Okay, let me give you one more example to finish this one off. And as I said in the previous on the previous page, we think of that integral being posed in terms of this independent variable x, but I called it the thickness variable. And the reason I call it the thickness variable is because you can rotate this thing around horizontal axes as well, and it still works, right? The cylinders, that instead of being straight up and down, they might be, on their side a little bit. So let me show you what I mean. So example 2. So the region, so we always sort of start with this thing, the same explanation. You probably have it memorized by now. The region bounded by the curve. We're going to use the same curve, the square root. We know why. I love to draw it. The axis, or sorry, the x-axis. And x equal to 4 again. So the same region. We're going to revolve this around the x-axis now. to generate a solid. Okay, so find the volume, or find its volume. Okay, so basically it's the same picture that I had above. I'll redraw it as soon as I'm confident that people have really copied this down. But now instead of rotating around the y-axis, you're going to rotate around the x-axis. And have no fear, we can still do this. It still works out quite well. So let me skip over to the next page so we can start fresh with a nice drawing. Okay. So here's the square root of x. We've got our blue curve delineating the endpoint of this thing. So that's at x equal to 4. Still doing this, but now in this case, we are rotating around the x-axis. So if you think about this, what do the cylinders look like that are going to make up this Riemann sum? Well, the sort of the object that's being formed is sort of coming out this way. And so that means that we're going to sort of fit our cylinders, our little Russian dolls. They're going to come in like this. So that means that the rectangles that form the Riemann sum are going to be horizontal as opposed to these vertical rectangles. We can skip all of the sort of Riemann sumness of it all, and we can just find these infinitely thin cylinders. But let me show you what happens, right? So you might have a cylinder that looks like this. So this line right here that's on the board, and it's rotated around like this. And then I move up or down a value of y, and I rotate that line around, and so on and so forth, right? And so I pack these things on top of each other in this horizontal manner. Okay, so then the question is, what is the distance here, and what is the radius that is formed right here? We have the value y here, which tells us that the radius of this cylinder, the distance from the center, the x-axis, up to this curve here, this is given by y. So that tells us that we are going to be posing this integral in terms of y. So the question is, what is the height of this cylinder? So what is this right here? And the question really is, what is this point on the curve right here? If we know the value of y, how do we recover the value of x? Well, we can invert this function, and we can say that x is equal to y squared here. So that means that this point is given by x is equal to y squared, right? We're on the curve. And so therefore, this distance down here from the end point 4 all the way over to this point is going to be, so this point is x, say, this is going to be 4 minus x, which again, we want everything's in terms of y. We know that x is equal to y squared, so we get 4 minus y squared in this case. Okay, this is good, right? Because this tells us that we now have the radius, y. We have the height of the cylinder, 4 minus y squared. Now we want to ask ourselves, what are the endpoints, since we've identified that we need to be using y? Well, we can see that one of the points where we start here is at 0. So one endpoint is y equal to 0. The other endpoint is going all the way up to this point up here. So that point is given by 4 in the x variable. Since it lies on the curve y equal to the square root of x, this is 2 in the y variable. So we're going all the way up to 2 there. So our second, or our upper endpoint, is y equal to 2. And then the axis, well, the axis is the x-axis. That's given by y is equal to 0. So luckily, again, just based on how these examples worked out, that means that the L value is going to be 0. So now we've got all the pieces we need. We can see that the volume of this thing is given by a definite integral, 2 pi times the shell radius. So we said the radius is equal to y, and then times the shell height, which we said is equal to 4 minus y squared. And then the delta x term converges to that infinitesimal dy, so the change in y. So this gives me, if I pull the 2 pi out front, 0 to 2, and now I have 4y minus y cubed that I'm integrating. And so, oh, I'm sorry. So now what I can do, again, just a nice, easy polynomial. So I get 2y minus y to the, 2y squared, y to the 4 over 4, running from 0 to 2. Again, nice calculator problem. This is equal to 8 pi. So wasn't that interesting? Wasn't that exciting that we were able to, even though we sort of expressed the general formula in terms of x, there's nothing special about x. And we've seen this before, right? You can always do these Riemann sums in terms of y as well. The hard part a lot of the time is inverting the function. For us, for this example, it was relatively easy to invert the function, so it wasn't too much of a problem. And so just to close off here, this is usually what differentiates using either the volume method or the method of slices. And essentially what it comes down to is what ends up being easier mathematically, right? So you're going to end up having to invert some function that you probably don't want to have to invert like we did in the previous video. Then that means that you should use the other method. That's really how you can choose them. Now, as we go forward in this class, I'll probably tell you which one to do because we need to be tested on both of them equally. But, when it comes to doing this stuff in practice, a lot of it comes down to, what makes our life the simplest, because not all functions have inverses, or at least inverses that we can write down in a nice compact manner. Okay, so thank you, and I'll see you again for the next video.